Okay, so good afternoon, everyone, and thank you for joining us today in our Energy Managers Community of Practice meeting. Today, we are going to talk about decarbonization and high-efficiency electrification of heating systems. With me on the call is Lucas Glaspel from Train Account Executive, and I'll introduce him shortly. But as usual, first, I wanted to start with land acknowledgement. Clean Air Partnership is a Toronto-based organization, and we acknowledge that the land on which we operate is the traditional territories of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. In our effort to be more meaningful when we do a land acknowledgement, we share a short video where we can learn something new about the culture and the life of Indigenous people. So I'm going to share this short video from Zalong Web, and he explains why do Indigenous peoples hold this land as sacred.
Ever wondered why Indigenous peoples hold the land or items as sacred? You might hear an Indigenous person talking about the sacredness of the land, but what do they mean when they're talking about the sacredness of the land? Well, for my people, the Anishinaabe, it all goes back to our creation story. We believe that our spirit, the spiritual part of ourself, comes from the sky world or other places, but our bodies, our vessels, they come from the earth. I mentioned in a previous video about how Indigenous peoples view Mother Earth as being one of our own mothers, and that's because everything that it took to create our physical self had to come from the earth. That's why we hold the land as so sacred, because it's what created us and it's what's going to create our next 7 generations. That's why as Anishinaabe people we care so much about the health of Mother Earth, because we know that what we put into the earth is what's going to be put into our future 7 generations. So why an Indigenous person might hold the land or items as sacred, it all goes back to stories. It all goes back to our creation stories. And miigwech for watching.
Miigwech for watching with me as well. Very briefly, 2 of our tools, the Climate Policy Database tracks climate-related policies across the CAC, and the Climate Action Atlas tracks implemented ambitious mitigation projects. This is beyond CAC, as we wanted to feature some great examples across Canada. I will share a link to these tools shortly in the chat so you can access them. Also, for our upcoming events this Friday, we are going to summarize everything that we learned from the Climate Governance Accountability and Implementation series that we held throughout the last year. And on February 21st, we are going to talk about affordable housing, energy, and efficiency programs. Now I wanted to introduce our guest speaker. Lucas is an account executive at the Train Technologies Toronto team, working closely with clients to achieve their sustainability and energy goals by leveraging their building automation system, BIS, supplying equipment, and optimizing the heating, ventilation, and air conditioning, which is HVAC performance. Through his leadership in low carbon and high efficiency HVAC strategies, Lucas supports clients to create and design HVAC solutions and follows them through manufacturing, installation, and optimal operation. Recent projects include a new district chiller heat pump solution with Noventa Energy to extract waste heat from public sewer systems and utilize it for building heating, as well as complete equipment and BIS upgrade projects for Ontario power generation buildings. Lucas' current specialization is in electrification of heating and building environment optimization with smart building automation technology. He also has experience in HVAC operations and services, building construction, and HVAC equipment and controls. Lucas actively empowers others to take a step back and consider the holistic picture in every project, supporting clients across Canada to achieve their sustainability goals with lasting results. Thank you so much, Lucas, for being with us today and for your presentation. You can take it away by sharing the screen.
Thank you.
I would just quickly remind folks that we're in the meeting because we want to encourage a discussion. Lucas is fine to interrupt him if you have a specific questions for the for the slides and for the system that he's talking. So either do your written question in the Q&A or raise your hand and you can just speak in. As you may know, we've booked hour and a half. If you need to leave, that's fine. We may also finish earlier depending on the questions that we're receiving, but really feel free to be more kind of like an engagement also opportunity to discuss what we are seeing and what Lucas is going to present. And I'm going to step away now and pass it towards you, Luca.
Perfect. Thank you so much, Desi, and thanks everyone for joining. Hopefully we can have a bit of a discussion here, and it's not just Lucas talking to a screen for an hour. But please do, if you have any questions, raise your hand or interrupt me. It's better to have a discussion about these things. And I really find from a learning perspective and conversation and just decarbonizing in general in buildings, having a discussion and having everybody share knowledge, we all learn more, and I really enjoy doing these presentations because I learn from others as well. So really enjoy these, and thank you for having me. The Clean Air Partnership is an incredible organization, and glad to be part of their team and learning from them as well. So just going to go through some slides today and talk a little bit about decarbonization, specifically kind of in Canada. I'm out of Toronto myself, but we have kind of a team across Canada that's working on this and different parts of it. The momentary kind of information on Train, just kind of the single slide to talk a little bit about kind of the organization I work with, and the reason I work with Train is really the commitments and the leading by example that they really put forward through the Gigaton Challenge, where they're reducing our carbon footprint of our clients by a gigaton by 2030, and that's like similar to France, Spain, and the UK combined in energy use, as well as leading by example in delivering zero waste to landfills and improving our water usage as well in our manufacturing, all the way into the buildings that we work with. So going all the way from scope 1 and 2, which we'll talk about in a moment, to also our scope 3 of our customers and also our vendors and suppliers as well. So making sure our entire supply chain is moving towards a net zero and positive environmental footprint, alongside the other parts of ES&G. So the S&G, especially looking at safety metrics, especially in our communities and workforce diversity, and also Train, we care a lot about gender parity in our leadership roles and across our organization, making sure that we see not only diverse groups across all of our different parts of our organization, but also across gender and different people's perspectives as well. So jumping into the pillars of decarbonization that I'm going to talk about today, really centering around 4 different pillars is the way that I really like to look at it from a building decarbonization standpoint. Really focusing on number 1, and we've been looking at this for 60, 70, 80 years now, really, is energy efficiency. How do we make more equipment more efficient, as well as buildings themselves? Let's save energy where we can. If we don't use energy, we don't have to make it, which means we're going to decarbonize as well as be more sustainable in general. Tying into that, as we move towards decarbonizing buildings, a lot of our heat comes from carbon-based fuel sources. So electrification in a lot of places where we have green grids, Ontario, where I am especially, Quebec, British Columbia, are kind of the big ones in Canada, where we see extremely low carbon fuels that power the grid. But even across the entirety of Canada, it's really impressive to see how green our grid is in comparison to other places in the world, and especially in comparison to the US. Everywhere is striving to have a cleaner grid, which thus allows for electrification to help decarbonize more. But in Canada, we are doing a great job, and the utilities are pushing for that year over year for improvement significantly. And so what we do at the building level will also be tied into what they're doing on the grid level and allow for a lot more effective electrification. And really proud to see that changing and improving in Canada continuously over the last decades. The other part is kind of tied into that as well, as the renewable energy that I was talking about in the bottom left corner. And then also a big part of carbon emissions is the embodied carbon of refrigerants. So looking at refrigerant management, and I will touch on a slide on refrigerants if anyone has any questions, and really just ensuring that we're picking the right refrigerants for the right job. You can have a refrigerant that is a low greenhouse warming potential, which is fantastic, but its efficiency might have an impact, which then causes us to use more energy, for example, which counteracts some of the benefits of GWP. So really picking the right refrigerants from a safety perspective, from an efficiency perspective, as well as a capacity perspective, and just ensuring that the confluence of all those different factors, we pick the right thing for the right task. Because every different type of heating or cooling system needs different types of capabilities as well. So just because we may have a wide variety or variance of different knowledge levels, I'll just touch on this slide really quickly. This is specifically the scope 1, 2, and 3 descriptions. So on scope 1, we're really looking at direct emissions. So thinking best of on the building level, a natural gas boiler that's making hot water, for example. When it burns natural gas, that would be scope 1. Scope 2 would be a good example of a chiller or a light bulb. Really, we're using energy at the site, but that energy is being created off-site. So that's in that case, the electricity is coming to the site from, for example, an energy generating station. And if that's burning natural gas at a peak time, for example, that's a scope 2 emission for that building. Scope 3 is a little bit farther down the value chain, either the clients or the vendors, usually like indirect activities that are not controlled by the company. A good example is something that you're purchasing as a building owner or something the tenants are doing. A great example of scope 3 emissions on the building level. If anyone has any questions or comments, please do interrupt me. Otherwise, I'll just keep moving forward, but I do appreciate and really enjoy the conversations. So feel free to interrupt at any time. I don't think I see hands for something. So if there is a conversation or someone looking in from a chat perspective, please interrupt me and just let me know. So quick as well on what heat pumps are, because there's a lot of different ideas and perspectives and kinds of heat pumps, but generally on how they work, there's 2 different modes of operation. So the top right corner that we're looking at, we'll see in this case, in heat pump cooling operation, this would be an air to water heat pump that we're looking at here as an example. It's running like an air-cooled chiller, if you're familiar with an air-cooled chiller. In this case, it's producing 42 Fahrenheit chilled water or cold water, and it's taking that heat out of the water and sending it to atmosphere. So you have 95 Fahrenheit coming into that air-cooled unit, and it's rejecting or exiting the unit at 115, 20-degree delta there, and that heat is being put to the atmosphere. Now, with a reversing valve, we're able to use a heat pump to actually do heating as well. So that same unit in a different mode is able to produce hot water with cold air coming in and even colder air coming out. So in this example, 120 Fahrenheit hot water leaving, and we have sub-freezing air coming into the unit and even colder air going out of the unit, just in this example. But there's many examples of this as well. And here's some other kind of examples of how heat pumps can work. So looking at this, there's air to air. Common examples are rooftop units, VRF units, a split unit in someone's house, for example, air conditioning unit that could be set up as a heat pump unit as well in a residential home. Then on the water to air, we see very commonly in a lot of commercial buildings, water source heat pumps. We also see them in residential high rise as well. Then we have air to water, which is the example I just showed a moment ago. That's taking heat from the air and then heating the water itself into the conditioned space. And then the last one here is water to water. Often water to water units, we don't see a reversing valve, which means that it's set up more as a chiller heater, where you're always producing hot on one side and always cold on the other. But there are some examples where we have a source side and then a hot/cold side with a reversing valve as well, where we can reject heat or pull heat from a source and never change and use a reversing valve to change that circuit. But it really depends on what you're looking for the system. Happy to answer questions on those if anyone has any questions. I got a couple slides on embodied carbon that I think it's important to touch on and get a lot of conversations, especially with energy engineers, on what is the embodied carbon versus the operational carbon or operational emissions that we see in buildings. So from an HVAC perspective, specifically around the heating and cooling equipment, I'll show that in the next slide, but we really do see a large swing towards operational carbon in the lifetime of the equipment. In this case that I'm showing right now, we have a hydronic heat pump chiller. So think of a water to water unit that we were talking about earlier. And that chiller here is a high amount of raw material. This information is actually from an EPD that we did, an environmental product declaration that we did for this particular piece of equipment, which definitely recommend asking for chillers and large equipment, especially that you're working with, if you have that in your specifications or clients that you're working with, or engineers that you're working with. So from the perspective here, we have raw materials, a huge percentage of the equipment. That raw material is really broken up with a high percentage of copper for heat transfer, obviously, and the steel to make up the unit, and a small amount of aluminum. And then in this case, it's actually quite a recyclable unit. So you'll see as we move around, the transport is a very small piece of the emissions of this unit for the lifetime of the unit, for the embodied carbon of the unit. The disposal emissions is fractionally close to zero. It's not exactly zero, but rounding to zero. And really that's because this is fully recyclable, other than pretty much just the controller and the wiring. It can be a little bit more difficult, the technology items that are in it to run it, and to kind of the brains of the unit. But otherwise, it's very easily recyclable, all the different pieces of the unit. And then the manufacturing, in order to form and create the steel and the copper, the aluminum, that's where we see that 16% in red there. And the leakage and charge are refrigerant-based emissions. So we calculate that there's an effective 7% leakage on average for refrigerant from the time it's made by the refrigerant manufacturer all the way to the time that it gets into the unit on site. So that's a calculated factor based on standards, experience, and all the different testing and stuff that has been done in the past. Ideally, leakage is 0%, but the reality is that things can go wrong on site, and so there's the risk, and that needs to be calculated and accounted for. And the charge itself is the embodied carbon. So ideally, that charge stays at 13% there, and you're able to recycle that at the end of life of the unit, and you don't lose the charge to the life of the equipment. But there is that risk there, which is the leakage as well. On the operational versus embodied carbon, a good example here, we got two circles. The embodied is at the top of each one. It's a very small percentage of the entire carbon emissions, and really that's because when we look at the equipment, the lifetime of it and how long it lasts compared to the carbon emissions of the grid, in this case for the use of this chiller, the grid is uses a lot more embodied emissions operational emissions than the embodied ones. So in this case, it's really interesting to see actually the difference between 2010 and 2020. We can see that there's actually an increase in embodied emissions, and that really is on a North American level. The reason we see that is the embodied emissions don't really change. They might have slight reduction actually, but not increase. But what we're actually seeing is, on average, the operational emissions have been going down. So over the last decades, we've been actually seeing the cleaning of the grid, which we talked about earlier, across North America, which is very exciting to see. And hopefully the 2030 diagram of this, once we get to 2030, we'll see embodied carbon taking up a much larger portion of this pie as we see the grid emissions reducing significantly over the years.
Lucas, can I actually bring you back the slide before?
Please do.
We had the question of if you can share the slide before, if you can share about the EPD for the chiller.
Yes, what would you like to know?
Diane, what exactly do you want to know? The question is, can you share that EPG for the chiller with us?
Yes, I can do that after the presentation. Not a problem.
Oh, okay.
Yeah, it's quite a long document, so I mean, if we have a discussion at the end, I'm happy to pull it up and we can go through it if you like. Otherwise, I'm happy to send it to you after, Desi, and you can distribute.
Okay, thanks.
No problem. Any other questions while we're kind of stopped here?
Not in the chat, and I
Okay.
didn't see hands, so we can keep going. Thanks.
Sounds good. So the next slide here is something that I kind of, it was really interesting and fascinating for me when I took a look at this. It's probably a few years ago now, 4 years ago. And I thought it was extremely interesting to see. So the legend along the bottom is different rooftop units. They're kind of different sizes and different capacities and technologies of rooftop unit that we have. And there's three major blocks. So on the left, we have efficiency improvement, and then on the top, refrigerant change, and then the bottom is conversion of gas heat, to heat pump. And what we saw, if you're looking at the black writing at the below of each box, what we found through our own testing and research, as well as third-party reproductions and looking at it, is that we are striving towards extremely efficient equipment. We've seen huge improvements in efficiencies, especially with Department of Energy requirements that have changed for 2023 previously at the beginning of 2023. We saw a big change and improvement in efficiency, but all the efficiency gains that we've been seeing is only equivalent to about a 3% improvement from a carbon perspective or greenhouse gas reduction perspective. So even though we're doing extreme improvements from a DX cooling perspective, because from a grid level perspective, the gas usage is very low, making that change in reduction in greenhouse gas potential really, it's only about 1 million tons annually in North America, which is not enough of an impact to make a big enough impact to do what we need to do with 3% improvement. So we also looked at refrigerant change. So we'll move up to the top right there. And with refrigerant change, also an extremely important thing, and we're doing it at the same time as we're looking at here, moving towards 454B refrigerant from 410A. 410A has a greenhouse warming potential of over 2,000. I think it's 2,200 and something. And 454B has a global warming potential of 466. So it's about 20% of what the 410A is, which is like a great reduction from a perspective for rooftop units. Great drop-in replacement to swap from the 410A existing units to the new 454B refrigerant new rooftop units that are coming out. But again, from a overarching impact life cycle of the equipment, it's only roughly 3% improvement. Again, it was around 1 million tons annually again of CO2 equivalents, which is just not enough. Like 6% isn't going to get us there. So the biggest impact that we really see, and what's kind of amazing, is this bottom right corner, where we looked at even a 20% conversion of unitary gas heat to heat pumps. So that would be a DX cooling, which is using refrigerant from a cooling perspective, and then gas heating, which is the standard rooftop unit we see in every building, kind of small, medium rise that we see around North America and absolutely all over Canada. Even if we took 20% of those and made those have heat pumps in them, we'd see a 16% reduction in CO2 equivalents. So all of that GHG reduction is really coming from the removal of gas heat and doing that heating with a heat pump. And we have rooftop units that we work with every day for many years now that are able to do that, and all the manufacturers do. It's a product that is very easy to work with and very easy to replace existing rooftop units with. And by doing heat pump, even with a gas backup, you can do a huge reduction in CO2 equivalent. So I thought that was a staggering amount, and really goes to show that any way we can reduce our gas usage is going to have our biggest impact on GHGs. I have this slide here just to show kind of different things that can be heat pumps, that not everyone remembers that really a heat pump can be any type of equipment that you would have in a building, whether you're looking at VRF systems, rooftop units, large or small, water source heat pumps kind of at the top, to your applied units, which are your air-cooled chillers or heat pumps, or water-to-water units. There's simultaneous heating and cooling units, etc. And you can also have custom air handlers with heat pump technology built into them. We do those quite a bit now, as well as the cataloged and semi-custom air handlers with heat pumps as well. So there's a lot of great technology there, and you can have a heat pump almost look like any type of heating and cooling equipment now. It is kind of ubiquitous with that. This is a great rule of thumb that I really like to touch on. And what we're looking at here is a slide of just showing the efficiency improvement of heat pump equipment as the temperature or the lift, the difference between the outside air, for example, and the inside air, as that difference reduces, we see a lot more efficiency. So in this case, it's air to water heat pump making hot water. So a standard air to water heat pump that's producing, for example, 140 Fahrenheit, or a water to water heat pump that's producing 140 Fahrenheit hot water. If we're able to reduce that temperature, we see a huge savings or improvement in efficiency. And so what we found as a rule of thumb is every 1% Fahrenheit increase in temperature above a hot water temperature of 105, every time you increase the temperature a degree, we see a roughly 1% efficiency hit to the piece of equipment, which means more electricity needed, which means higher cost to run the equipment, and also higher greenhouse warming potential or greenhouse gases. And so in order to combat that, as we move away from natural gas boilers, we really need to move away from the 160 or 180 Fahrenheit hot water and move towards low temperature systems. And so with that, we've done quite a few studies on hot water supply temperatures that are needed for different types of equipment, because in Canada, as we know, the expectation is it's very cold outside. Even though we have a beautiful day today, we would expect that it does get extremely cold in Canada and northern US as well, but especially in Canada. And with that, we need to ensure that we have enough heat going through our terminal devices or our air handlers in order to be able to provide enough heat in the space for the people that are there. And what we found is that the temperatures that are needed in the space are much, much lower at the terminal devices than is currently being provided by boilers. And the reason for that is that boilers were just always kind of set to those temperatures to run best for a natural gas unit, and not necessarily what was actually needed for the building. So what we found is that you may need to replace a coil, for example, or if you have an end-of-life piece of equipment, you might replace the end-of-life piece of equipment, or you might even just reduce the temperature of the space of the hot water, and then check the space and see how it responds. Sometimes you have properly sized coils for lower temperatures than are currently there. So you can use the existing coil in a lot of cases too for at least a lower temperature than currently running. But what we found is that air handlers especially can kind of go to extremely low temperatures that you see here in the diagram. And even VAV boxes and fan coil units and kind of single zone VAVs, we're really seeing air handlers kind of, you can see those low temperatures still operating. And so we're seeing a lot more designs coming out in those low temperatures, 90, 100, 90, 105, 95, 110 kind of temperature range. We're seeing those low temperature hot waters still supplying the same supply air as needed from the coils inside the spaces. I was actually taking a look at a building the other day in Winnipeg, which is freezing, as you know, very often. They get minus 40 Celsius hot weather in the winter. And in that case, with the building we looked at, had been operating at 100, 110 hot water with heat recovery chillers for the last 35 years. So since they built the building, they'd been running that downtown commercial building in Winnipeg and never have issues even on the minus 40 days. So it was a great example for me of, hey, this building's been running for decades with no issue. And really interesting to see that hot water does not need to be as hot as we think it does. Any questions so far? Okay, great. So the next thing I'd like to step on is kind of where you get heat. So the way heat pumps work is that they don't generate heat. They're not a heat generator. For example, a natural gas boiler burns gas to make heat. A electric boiler uses electric resistance of the electricity traveling through a resistor in order to heat up a space. Whereas heat pumps actually move heat. So they take heat from one place and they transfer it to another, usually at a boosted temperature. From a low grade source, for example, heating from outside air when it's cold outside, and boosting that to a higher temperature inside the space with an air to air unit. We also see that heat being pulled from lakes, rivers, ponds, some great examples right now. And with the N-Wave systems in Toronto, storm and sewer, there's the Hoover heat exchangers, and Toronto Western Hospital is doing a cool project pulling from sewer. Geothermal projects we see all over the place, and many are familiar with already. There's a lot of those projects going on for many decades now, and especially the last 10 years, we've seen a huge increase. And then storage sourced heat pumps or thermal batteries are very commonplace now as well. And then the last one I meant just to mention at the top is really just recovering heat from other places. If you have a cooled, chilled water load in the winter, using that heat and using it to take advantage of instead of sending it out to the space is really important. So I have this slide as well. It kind of going back to storage. I find it really kind of a interesting thing to think about, and an important factor as we move towards electrification. So we see carbon-based fuels, in this case, coal and oil on the left, really used to store fuel. Natural gas is a great storage fuel as well. There's energy stored in fuel form. But with the electricity, it's instantaneous. So we have to figure out ways to store. A lot of people look at lithium ion batteries, but there's a lot of inherent risks and problems with that, and cost as well. So another way to store electrical energy is actually through heat. So one thing that we do a lot is thermal batteries. So I'll show a couple of slides on that. I think it's technology that's extremely valuable. We've been doing it for about 50 years in the industry with cooling, but we're now seeing it a lot happening with heating as well. So I'll walk through a couple of diagram examples of that. And if anyone has any questions, happy to answer them. So this is a fairly straightforward example here, air to water heat pump, or an air cooled chiller in this case, doing cooling of cooling coils. You can see return water coming back, and it's just doing straight cooling. The next picture is heating with that same unit. So it's heating coils. Again, very straightforward, air to water heat pump, directly heating and cooling. What gets interesting is as we move towards the using thermal storage, we're able to take advantage of thermal batteries. So in this case, instead of running a chiller for cooling, we can actually use thermal batteries with very low electrical demand. We just need to run the pumps, and we can actually use thermal batteries. In this case, these are ice batteries. So what we're doing is we're taking phase change of water, and we're freezing, it's frozen water as ice, and we're running glycol through that to cool these coils. And now we have a chilled water load. So now we're able to cool the building without running a chiller, which saves the electricity on peak demand days, and also allows us to size the chiller a lot smaller because we don't need to run it at the peak. The other side of that is that we can use these thermal batteries at different other times of the day to do heating. So now instead of running a natural gas boiler, you can use that chiller or water to water heat pump to actually make heat instead of chilled water. So what we're doing here is we're on the one side, we are making a chilled glycol to freeze those tanks again. And what we're doing is we're pulling the heat out of these tanks. So now the tanks, that heat is coming out of them, they're freezing. That phase change allows for an enormous amount of energy stored in a small space instead of having a large pool or a large tank of water just moving temperature 1 degree up and down or 5 degrees up and down. We're able to do that same 32 Fahrenheit or 0 Celsius change, but we're doing that at a very, very compact way with changing the phase or freezing it. So by freezing it with this chiller, we're able to then take that heat out, and that heat then goes to the heating coils and produces hot water. So now we've been able to decarbonize this building or this system with hot water coming from the heat pump or the hot water chiller, and not having to run a boiler system. So taking advantage of those thermal batteries. This can be done kind of simultaneously and in quite complex systems whenever needed. It can be very simple. It can be more complicated. It, however, needs to be set up for the building or the campus level, or however you want to run it. But what we found is that adding thermal batteries to the system allows for a very efficient way to store energy for other times of the day or peak periods where it's needed. Excuse me, any questions on that so far? Okay. So I guess one kind of thing I like to talk about and question I have when we look at rooftop units, and I have a slide here on rooftops, is this is a very common piece of equipment. And what I found is that when you want to switch it to a heat pump from a DX cooling gas heat, which is the most common cooling and heating piece of equipment, a lot of concerns come around. Okay, is the unit a lot heavier? Is it a lot bigger? Is it going to fit? All these different things. And I like to show this slide because my question is always, this is a heat pump rooftop unit. In your eyes, what is the difference between this and a standard rooftop? And when you look at it, you'll come to realize that really the heat pump rooftops, as we use as standard heat pump rooftops from the factory, don't have anything different. They're exactly the same setup. What is different is inside the control logic. They're controlled differently. And then we have a reversing valve inside there that allows us to run the refrigerant in a different way. So there's a slightly higher cost in order to be able to set up the unit in that way. But it's marginally larger and really it makes it a very easy swap out, especially with our dual fuel units, which use gas heat as backup and heat pump as primary source of heat. We see in Ontario, at least, a lot of Enbridge incentives right now supporting that. And we see that those units can be very cost effective and easy to replace and swap out for existing units. So we're seeing a lot of heat pump rooftops being replaced or replacing existing rooftops right now.
Lucas, there were a couple comments, and it was a couple slides earlier, but I see that
sure.
Let's go back. Kind of like have a conversation here, but the proposed lower temperatures do not take into account the fact that higher airflow would be required to deliver the same amount of heat or the limited surface area of existing radiators, which means that existing radiators need to be changed.
Great comment. Yeah, exactly. So when you look at these, and I did mention that when I was speaking about this, but absolutely. So when you're looking at these replacing coils, making sure that your fans, for example, can handle the static pressure drop, extremely important and all part of design conditions in retrofit applications. In new building applications, this is quite easy because we just design for it. But in retrofit applications, we need to make sure that everything is set up correctly. On the terminal device side, if equipment is at end of life, we often see the transition there. And in addition to that, we see on just looking at from a perspective of dropping the temperature, you might not get down to these low temperatures that we have here as minimum design recommendations, but going from 180 to 150, for example, we commonly see building operators able to drop the temperature of the hot water supply without doing really any work or changes, or maybe changing out one coil on a single unit, for example, that is causing the most issues or was kind of undersized in the space in comparison to the other ones. But we do see that, or like I've seen at least from experience, when you go into an existing building and start looking at what the existing units are able to manage, the temperatures that the buildings are often operating at are a lot higher than needed. A good example is one that's operating at 180 degrees. I was in there last week looking at that. unfortunately, like no building operator and not well managed building, but the existing boilers were producing 180 and they were just turning on and off, cycling all the time. And there was a 1 degree delta T on the hot water supply return. So it was 180, 179 return, which is extremely inefficient and not good for the life of the boilers either. But a good example of that building, that there's some work that can be done. We can potentially reduce the temperature if we wanted to move towards heat pumps. And we also there can be a lot of efficiencies found just by managing and controlling that building with a proper control system as well. Just as an example. A little off topic.
Kind of like a follow-up here, comment the questions. Yeah. Are there issues with the SW Ontario HVAC contractor knowledge based with regards to this lower temperature systems? Do they all know how to deal with them properly with regards to specification, installation, and maintenance?
Yeah, I guess I wouldn't use the word issue. It's a great question. I think all of us are in the industry across, no matter whether it's contractors, consultants, owners, property managers, manufacturers. Everybody has been learning every day, and I think there's a very wide range of knowledge, experience, and just expectations as well across the different parts of the industry, as well as different parts, even different markets. Do work kind of in different places in Canada as well, and different specific areas have different expectations and knowledge as well. And some are moving faster to decarbonizing or faster to low temperature systems versus others. A good example is kind of just across the border in New York right now, we're seeing a ton of low temperature systems, kind of in the 90, 95, 85 temperatures. They're really pushing towards that because they need incredible efficiency and they're moving away from gas very rapidly. We're starting to see that in Toronto, as an example, locally in Toronto here. I mentioned the building in Winnipeg where they've been doing it for 40 years. Vancouver, they have a lot lower temperatures. But it's really depends on where. Montreal has been doing some really cool stuff as well. But you kind of get outside of certain geographical areas or certain knowledge areas, and there's different perspectives. And I think generally, like, everyone's learning. Like, a lot of this is kind of old technology or old perspectives, but looked at it in a new way. For example, the thermal storage batteries that I was talking about, they've been around for 50 years. We've been using them for 50 years as cooling, but no one ever just used them for heating, even though it's the exact same thing. They're still freezing and then thawing, freezing and then thawing. Nothing changes, but we use the heat out of the condenser of the water to water unit, which no one ever did before. They just used it for cooling to save energy and save money. So now as we move towards decarbonizing, it's using the technology that we have just in a way to make heat and reduce carbon emissions as well.
Thanks.
Does that answer the question?
Yeah, I think so, yes. I'm gonna move you back to the, sorry, there's another question related to that. And then there are a few questions on the
Let's do it.
On the heaviness. That was, you finished there before I interrupt you. But going back to the lower temperature, does piping often need to be changed in any way to upgrade an old system to lower temperature system, like higher flows and scaling?
Great question. It's something that needs to be looked at. I highly recommend the consulting engineer that you work with to take a look at that. Is usually best for that work. Sometimes I'll get involved as well with it. The answer is sometimes. It depends on your current design, the amount of temperature drop that you're looking at, and what's needed. It's completely depends on what was originally designed and to compare to what you're going to. So yeah, it depends.
Right. Thanks. And now I'm moving you to the where you before I interrupt you, the slides were on the weight. So the question is, there's no additional weight for HP and RTUS for heat pump RTUS, and then a follow-up comment if you want to hear that.
Yeah, not really.
Yeah, heat pumps RTUS must have oversized GX in order to provide reasonable amount of heating at cooler outdoor air temperatures. Can increased weight require structural modifications?
Absolutely. So yeah, two parts of the question. So in the first part, the weights, yeah, like it does, there's not a big impact. And the reason is that we're not changing, and it ties into your second part of the question there. We're not changing the condenser or the air to air portion that touches the outside air. In this case, we're using and we're sizing the units to the cooling load. Once it gets too cold that the heat pump is not able to keep up to maintain the temperature in the space, we move to gas heat or electric resistance heat. And now the reason we do that is it makes it a lot easier for retrofit applications. So in this case, in the picture I'm showing, most common rooftop in Toronto, GTA, Ontario, even the most common rooftop in, I would say, most of Ontario is a DX cooling. So that's electricity used doing the cooling, and a gas heat unit. Now, if we wanted to swap that out to a heat pump, if we wanted to make a larger condenser and have it fully electric heat pump wise, we would have a lot of negative effects on the existing situation. So the negatives would be, if we did that, would be more weight. It would be more electricity usage. We'd have to upgrade the wiring to the rooftop. We might have to upgrade the breaker, maybe even the panel. There's a lot of different things. We might have to do structural for the weight. The size would get bigger. All these things are negative impacts. So what we do instead for a lot of retrofit applications is we keep it the exact same size as from a cooling perspective as the existing unit. So the electricity stays the same, the weight stays the same, all within margin of error here. Breakers stay the same, panel stays the same. We don't change anything. But what we do is make that existing unit a heat pump. So it's able to do heating mode down to a certain temperature. Usually we see it kind of can maintain the temperature down to around -3, -5 Celsius before it usually kicks in to gas heat. And it does that with the existing sized cooling coils that it has there. And so you're getting that kind of free decarbonized heat in quotations. You're getting that from the perspective of without any change, minimal change to the unit. It's very easy. Contractors know how to install them. Nothing changes. They can just put a roof curb. If it's already there, the adapter curb or right on the curb, even sometimes. Take the old unit off, put the new unit on, reconnect the gas, reconnect the electricity, and you're good to go. And so with that capability, it makes it a lot easier, a lot lower cost to decarbonize, and you can do a lot more rooftops for the same price. And that's why we do it. And then you have that gas backup the same way you did have gas heat before, but now you have gas backup for the colder times. Great example this year, the times it's been where you actually would need the gas heat is super minimal. Like maybe what we call maybe 10 in GTA, 10 days this year where you would have needed the gas maximum. It's been extremely warm winter, but really the heat pump works for all those seasonal times as well as a good portion of the winter as well. And you have that gas heat for backup for the other parts.
Thanks.
You're
There's
welcome.
one more question, but I see also that there's 10 minutes to the 1 hour. So maybe we'll take this question a little bit later so we can cover a little
I'm
bit.
happy to answer. It might as well, if it's there, we might as well do it. No worries.
Okay. So can you explain how HVAC systems are adapted to handle extreme weather events such as heat waves and ensure reliable operations during power outages or disruption? And kind of like a follow-up question, with the warmer temperatures leads to higher humidity, does HVAC systems can work as an effective dehumidification and have these capabilities to maintain indoor air quality and prevent mold growth?
Great question. Two parts, and I might forget part of it, so let me know if I miss anything, please. But to answer your question directly, the heating of heat pumps isn't necessarily affected really by the kind of those temperatures in the summer that you're talking about, high humidity, high temperature heat wave situations. So really we look at the cooling as the issue there, right? And maintaining the cooling that is needed. So for that, to maintain the cooling, these heat pump units are set up primarily to be able to handle the cooling just as much as the heating. They're heat pumps in the word, but really it's a DX cooling and heating unit with gas backup or with electric backup. That, like, when we say that, that means that as long as you size your unit correctly, which means if you need 12.5 tons at your heat wave peak cooling load, and you put a 12.5 ton unit in there, that unit will meet the load. If you needed a 15-ton unit, but you only put a 12.5 ton unit, then your unit's going to be too small. But normally what we see is that the consultants are very good at calculating and working with those requirements to make sure we size the equipment correctly. The only issue I've really seen is I do actually quite commonly see older designs sometimes where they're oversized and there's more cooling capacity than needed. But I think that's gotten a lot better over the years as more calculations kind of have been found and we're able to get kind of more accurate pieces of equipment. But generally, like heat waves, if you have an existing unit that's maybe 20 years old and it's not sized large enough to handle the cooling requirements in the hottest parts of the summer, it might be time to look at, when you do look at replacing, to look at a slightly larger unit that has a slightly larger capacity of cooling to be able to handle your cooling load.
Thanks. There are more comments, and I encourage everyone to continue either chat and provide comments or with questions. But for now, I think, Lucas, you can continue with the presentation.
Okay, sounds great. No, awesome questions. Please keep them coming and comments. Would love to hear them. I unfortunately can't see them, but hopefully happy to discuss anything that is helpful. I'm just going to go through a couple example pieces of equipment. I don't really want this to turn into it's not supposed to be a marketing or really anything perspective, but it's more just to show you kind of what's in the industry and like what's available. So I'll just go through a couple examples of that. And if anyone has any questions on technology wise, how that works, happy to discuss them. But this is a good example of an air to water heat pump. Looks like an air cooled chiller if you're familiar with them. It looks almost exactly the same. And in this case, like, we can make 140 degrees hot water, large packaged units, kind of in the 2500 MBH of heating. If you want to think of it as like half a truck bed, in a long haul truck bed kind of thing, is the size of this unit. Excuse me. And it can do chilled water, hot water, whatever is needed, as an example. We also have a lot of modular units. We see modular as a great retrofit application, especially for heating and cooling and heat pump technologies. And we can see really high temperatures, 130, 140 Fahrenheit coming out of them. And in some cases with our next gen units going up to like 150 Fahrenheit, and doing that at cold temperatures. In this case, this one's 0 Fahrenheit, but with our next gen units, we're looking at -20, -30. As we see extremely cold temperatures, being able to still do hot water. This is an example at downtown location where we did 2 installs. The first one in front's a test unit, and the one behind it is more of a manufactured unit, as you can see. So you can see the different kind of protection just in wiring on these units, just as we're testing them out and seeing how they operate. But in this case, these units are about from 2 years ago, this picture now, or 2 winters ago. And these are operating extreme cold climate capabilities down to -30 and able to produce hot water kind of in the 155 Fahrenheit hot water perspective to replace boilers. This is a good example of like a 6-pipe unit. So when you have geothermal systems, we see these a lot. One of these building set of pipes is a building loop for the source. That would be the geo. You usually see like 25% glycol in there going to the geo field. And then one set of pipes is the heating and one set of pipes is the cooling. So we can make hot water and chilled water simultaneously, as well as pull and send heat to the source. Here's a good example for larger systems where we can actually see hot water. We're doing this a lot of district plants or large commercial buildings. We can make hot water up to 180 Fahrenheit with large centrifugal machines now. and make chilled water simultaneously at kind of in the 38 or just above freezing Fahrenheit. So really nice turn down, really good control, and able to produce good quality heating and cooling with different 6-pipe, 4-pipe units, whatever is needed. The technology is kind of standard now for those. And then on the booster side, we can do really freezing stuff. We do a lot of ice rinks now. So we're seeing a lot of municipalities move away from kind of the built up ammonia systems of the past to more packaged systems that can go even colder and a lot more efficient and also lower capital cost without needing the operational costs that come with kind of the built up systems. So seeing a lot of packaged units now for ice rinks doing super cold ice making, and they just kind of run forever, which is great. And we use those on the other side. We take that heat and we're doing hot water, so we'll use that to heat up domestic hot water for showers and hand washing and things like that. And then we also in some cases can take that heat and send it to other buildings too for hot water heating for the building itself for comfort applications. Doing that quite a bit and seeing that as a very kind of successful thing for customers because extremely reduces the amount of operational costs to maintain these the pieces of equipment because the package units are a lot easier to a lot less kind of maintenance and they don't need to be rebuilt every few years and they can operate really effectively at low and high temperatures. In this case, we have package units now that can go up to about 120 C or 248 Fahrenheit and produce extremely cold, like minus 20 Celsius glycol as well. So very cool units and we're really proud of the technologies that we have there.
Lucas, 2 questions on the last 2 slides.
Sure.
The one for with the changes in the refrigerants specifically for R410A in January 2025, will there be a shift of ASHP after that refrigerant shift, or will the R410A still be okay considering the low volume requirement per unit? Sorry, that's a lot of acronyms here.
Yeah, I wish I could. I don't know.
Do you see
I'm gonna see if I can
question?
pull up the question somehow so that I can.
Yeah, I will do it in the chat for you.
Oops, don't leave.
Or if
I can't find the chat here. Sorry, just do you mind repeating it? But instead of counting out the numbers, just kind of make it like a longer number.
I think Raphael, I was just going to ask.
Okay, great.
Hi, Lucas. I was just wondering because we know that there's going to be a shift in refrigerants by January 2025. And one of the refrigerants being obsolete is R410A. Now we do have current projects with the air source heat pump replacements that all the selections are designed based on R410A. Now my worry is with the shift of refrigerant by the time of construction, all our air source heat pumps are going to be R410A. Will with this replacements be affected? Like what I'm hearing is because air source heat pumps require low volume refrigerants that they should be okay. But I just wanted to see your perspective on it.
Yeah, so the truth is that no one really knows yet exactly what is coming out there. It hasn't been finalized and made public yet by the governing agencies. So I can't tell you exactly based on the size what's going to happen there. But what we do know is that 410A is going away and it's moving towards low GWP. We don't know that like what we're doing, at least at Train, is we're actually transitioning all of our equipment right now. So an air source heat pump, depending on what you're doing with that, I don't know what your supply is, if it's going air to water or air to air, and what your sizing is, for example. Like I don't know your exact details of your project, but for our equipment, our air to water units, we've really transitioned almost all of them already to 454B, which is the lowest GWP. The other one that's in the market is R32, which you might have heard of as well. That has a GWP or greenhouse warming potential of 630 or 677. So it's about a little less than double of what 454B is. And we've moved to 454B for the reason of it's the lowest greenhouse warming potential. So kind of best for the environment there. And we're doing that right now. So our air to water units, we're transitioning them already. Some of them, or most of them, have transitioned to 454B already, and the last ones will be in the next few months. For the smaller units, especially the rooftop units, like I was showing pictures of the rooftops earlier, those units are transitioning over the next year. We expect by the end of 2024, most of our units will switch from 410A to 454B. Now that's Trane. Some of the other manufacturers I've noticed are a little slower. Not that they're like not focusing on it completely as well. I'm sure they are. But seems like their announcements that they've just been a little bit delayed, trying to catch up on those moves and moving towards newer refrigerants that lower GWP. We have seen announcements from most of the other manufacturers also going to 454B for the clear reason of the low GWP, but we haven't seen them announce kind of as much as we have when they're going to actually have moved over to their new refrigerants and their different types of equipment. One thing we are seeing as a risk and a problem is if you do use VRF systems, which Trane has VRF systems as well, is that as you move to the 32 or 454B, those are A2L refrigerants, which are considered slightly flammable from ASHRAE standard. When you move towards that, you're likely, we don't know, there's kind of a lot of information coming out that like in the last few weeks even, but you're likely going to have issues with putting those into buildings. So from a VRF standpoint, we're going to see probably that move towards more hybrid systems where there's more actual water traveling around the building instead of VRF. And that might come with code compliance issues as well as we move towards replacing existing VRF systems. But we don't really know yet to be straight up with that all this information has kind of been happening over the last few years. And there's a lot of discussions between governing bodies, manufacturers, stakeholder groups across the industry and building owners, et cetera, municipalities, everyone. So there's a lot of conversations, but the clear understanding is that we want to have safe systems that reduce the greenhouse warming potential as much as possible and do that as quickly as possible. So that's why Trane's moved to 454B, and we're doing that as quickly as we can in all of our equipment. And really by the end of this year, we expect to have pretty much everything transitioned over, especially in our medium to large units. Happy to, if you want to discuss your existing projects, happy to help you out. And really, like, it's fairly easy for myself or one of my colleagues to give you selections. If you send us the 410A selections or information that you have on the equipment you have, we can send you back a 454B option as those come out in the next few months. We can't do a lot of them yet, but they are coming. So as you send, if you send those to us, we can send you an option back. So you can send that to your consultants or your contractors and say, hey, here's an example unit. You don't have to buy this exact unit, but here's an example unit that has a refrigerant that we want in our buildings. Just as
Thank you
an
very,
example.
thank you very much. Fortunately, actually, our basis of design are all Trane. And just for everybody's information,
Great.
we are replacing 11 RTE units and wanted to add that structurally, we do not have, like, I didn't see any major structural upgrades. So Lucas was correct in that sense that, like, it might be a case-to-case basis, but just specifically, for example, 11 rooftop units didn't require any major structural additional upgrades for our community center. Thank you.
You're welcome. Sorry, who's speaking? I can't see any names, so I'm just curious who was that?
Sorry, it's Rafael from the city of Markham.
Okay, Rafael. Great to meet you.
Thanks, Lucas.
You're welcome.
Thanks so much, Rafael, for jumping in and helping me with this question.
Thank you.
Thank you.
And Lucas, the next question is for the slide after this one. And the question is, can the technology integrate community centers pools with adjacent ice rinks? Perhaps use rinks waste heat to preheat pool heaters, kind of like a heating loop.
Absolutely. Do those all the time. Happy to work with you or talk to you about it if you want to know more information. Or you're welcome to connect myself with your consultant if you work with one specifically. But we're doing a ton of those. It's very common, very efficient, and that's the future for sure. You should be able to, if you have, like, every community center, if you should have a pool and an ice rink, and the efficiency is incredible. by taking advantage of both of those with heat recovery. It's funny, people complain about their pools being too cold, but I think that in the future it's going to be that at least in the warmer times that the pools are going to be too hot. So people will be happy. Your hot tub will forever be hot, but we can absolutely do that. There's no issues there.
These are the questions so far.
Cool. Okay. I can keep going. I don't have a lot of slides, but I did want to show one on refrigerants. I know we've talked a little bit about it, but I think it's a good, interesting thing just to kind of summarize where the industry is going. So I think it might be of interest to you. The black or dark gray here are refrigerants that, as you know, we've transitioned out of. You might be familiar with R11, R12, R22. Those are your low pressure, medium pressure, high pressure refrigerants. The next generations of those were 123, 134A, and 410A. Those either have been transitioned away from or are about to. 123 is gone now. 134A will be gone by the end of the year. And 410A, we expect to be gone very soon as well, as I think Raphael was saying there. So the next, what comes next? What are people doing? And what we're really seeing here are decisions based on efficiency. So that's over here, the COP of the natural efficiency of the refrigerants themselves, and then global warming potential. So what we see here in the low pressure side, it's been very easy, I guess easy in quotations, but it's been much easier to find replacements. There's a lot of companies that are working on replacements of super high efficiency, low GWP and low ODP, which is ozone depletion potential units. So on the low pressure side, that they've found a lot of technologies. We see 514A used quite a bit, which is a low GWP of 1.75. And we see 1233ZD, which is one. And we use both of these for different applications. They're good for different things. And we see both of those quite a bit. But as we move into higher pressure, it gets more and more difficult. And there's a lot of engineering and kind of chemistry that is still being done to come up with new solutions for these. What we're seeing on the medium pressure side is currently a lot of people working with 513A to replace 134A. It is a significant reduction in GWP, but obviously not really where we want to get to long term. It's still fairly large. But what we're seeing in these medium pressure machines, that these are your kind of, think of your screw machines as most commonly, or even your centrifugal mag bearing machines are usually medium pressure because they run at higher velocities. So what we're really seeing is 515B as well as a key transition there, where we're using it in some applications, especially hotter water temperatures. We'll see 515B and a move towards 1234ZE. The reason we don't see in North America, we're using this a ton in the UK and in Europe, but the reason we don't see as quick of an uptick in North America is really because it's an A2L, and it's got that flammable sign right here. This doesn't mean it's a fully flammable refrigerant. It's not like propane or natural gas, something which is flammable. An A2L is a risk of flammability. And I don't have the exact definition, so I won't tell you there, but it is a risk and needs to be designed for. So normally we're seeing people still stick in this blue range for medium pressure. On the high pressure, it's a similar problem, except there's not even one at GWP of 1 right now. So what we're seeing the entire industry right now, especially on rooftops, move towards is really this R54B moving towards 466. And we've seen a couple manufacturers move towards R32, which is a higher GWP. It's a slight increase we've seen in COP, but it's so minimal. It doesn't really affect the units that much. We haven't really seen it impact, but the GWP is so much higher. It's like only a little bit better than 466, and it's just like significantly higher than the 454B. So we've really been focusing on 454B and moving all of our units towards that. But what you're going to see in the industry is these two refrigerants probably moving forward in the high pressure side. So that's your scroll-based equipment, air-cooled chillers with scrolls, as well as rooftops, VRF systems, and mini splits. Okay. Any questions on refrigerants? Perfect. Okay. quick example. This is a cool system. Some of you might have heard of it, so I'll just show it. I like new technology, so I find it fun to show it as well. This is a slide from a company called Noventa, which is why I've got their thing here, because I did steal their slide. I have permission, but they asked me just to put their logo on it, so you'll see their logo on a couple slides here. But this is really cool. So we're pulling heat from wastewater in this case. They have this heat exchanger that is self-cleaning, which is really cool. It mechanically self-cleans to remove kind of films and black water that builds up on the sewer. And so you get clean water then going to heat pumps. In this case, we use like a train heat pump water to water unit to produce hot water. And kind of what we were showing before, we can produce steam, like 120 Celsius water under pressure, which can produce 14 PSI steam for humidification and things like that. And can also produce chilled water as well. Instead of having in cooling mode, like a cooling tower where the sewer is here, where this heat exchanger is, we can actually reject the heat to the sewer in the summer and not waste water either. So we're able to have a huge water savings when we're working on these types of projects. Here's an example of it kind of in a building for heating. We're able to pull heat from the sewer, boost it with the heat pump to the temperature that we need, and then serve the building without needing natural gas. We're seeing systems, depending on the building loop temperature, kind of between for higher temperature systems like 180, you might get CLPs kind of in the 3-ish range. But as soon as you get below 180, you get up to the 4.5, 5, 6, 7 CLP. Really, really efficient systems when we were able to take advantage of the wastewater, because the wastewater's already got a lot of heat in it. Here's an example at Toronto Western Hospital, just like local example project that we've worked on with Noventa. Huge savings in energy for the hospital campus. Large GHG reductions on our first phase that we did with them, as well as the amount of water is staggering. You don't really realize how much water you use to cool buildings in the cooling towers until you start measuring it. And with their system, you don't actually use any cooling towers anymore. So you don't waste any water or use any water, which is huge dollar savings these days. Water can be quite expensive. And it's also just much better for the environment. All that water can now be used for domestic purposes in the municipality, and they don't have to use it for a cooling tower. So really cool and very exciting.
Can we take some questions?
Yeah, of course. Yeah.
Go ahead, Patrick.
Thank you. You might have mentioned this. Sorry, I just tuned in quick. But how much did this project cost? I mean, 685 grand a year is amazing, plus the water savings. But I'm just wondering what the upfront costs were.
Yeah, so the cost of the hospital was a big zero. This was set up as an energy play for the next. I believe they signed a 30-year contract for the next 30 years. If it was, I think it was 30-year with a 20-year extension, if I remember correctly. But for the next 30 years, they're paying a flat rate based on their contractual agreement for heating and cooling for the hospital. And they've calculated this savings accounting for that. So getting these savings is after the cost that they're paying as well for all of that. And they paid $0 up front. That's the way Noventa goes to market, is that they say, we will pay the capital cost 100% and you get the savings. We just need to pay back our infrastructure investment. So very, very good for the hospital on that side. Like, they get those savings with $0 capital.
Okay, that's amazing. Thanks for clarifying.
Yeah, no problem. Yeah, great question. I didn't put it there, but that's how this company goes to market. They do like sell stuff as well, but really like where they bring their most value is kind of the full package. And they'll build a plant, which they did just behind the hospital here on Bathurst Street. And they're just finishing that up right now. But yeah, zero cost to the hospital campus. And they're doing like other phases with them as well to kind of help them plan for the next 30 years as the hospital expands, and uses that money that they save to put that into patient care, and I think a new tower as well, from what I've heard.
Go ahead, Ardell.
Lucas, just wanted to double check because with municipalities, we do raise like business cases for
Of
replacement.
course.
Now, just following up on pricing,
Yeah.
does Train have a data for pricing difference between like re and re for like compared to replacing it with heat pumps?
Yeah, great question. I would highly recommend you touch base. I can give you the contact for someone on my team. His name's Chad Sokolik, and he's a great contact for pricing and getting things together. We have that information, but I don't have that at my fingertips, unfortunately. And Chad's really the guy to talk to. So happy to set up a quick 15-minute call with him. And I'm happy to join in too to make the introduction and answer any technical questions. But he would be the best person to talk to about that.
Thank you very much.
Yeah, no problem. I don't know if my email will be available somewhere, but feel free to reach out to me and I can set up that meeting 15 minutes later this week or next week, whatever you like.
Great, thank you.
You're welcome. Any other questions? Oh, there's my contact right there. Look at that. I'm planning ahead. that was everything I had. I do have some appendix slides if people have more questions, but hopefully that answered all your questions and what you were looking for. Otherwise, I'm happy to continue discussing it. I do have till 2:30, so happy to discuss more. Even if you have a one-on-one, if you have a project specific you want to talk about or ask for advice on, I don't know. The way I'm set up, like within Train, is like I'm here to give advice and talk to people. It's not really. I'm not the guy that's kind of selling stuff. That's kind of other people within Train. So I am connected to the sales team, but really like my goal is really to help educate the market on the technologies that are out there and help decarbonize buildings as quickly as possible, because we can do it with everything we have. We don't really need anything more. It's just the act of actually doing it now, which can be a bit daunting. So that's kind of what I'm here to help with.
Thank you so much, Lucas, for the presentation and for answering the questions. It's great. And yeah, as Lucas said, we did plan this meeting for 1.5 hours. So we do have 15 minutes if there are more questions to be answered. Otherwise, I don't see, I think we covered everything from the chat. I don't see raised hands, but we can wait for a couple minutes if needed. But this was this was very informative, and you covered a lot there, so thank you so much for
it was a lot.
yeah, for jumping in. And I know that few folks also couldn't make it, but they will be listening the recordings, and we'll share with everyone the slides deck as well as the recording if you want to kind of like see what was covered, or if you missed something, or if you want a bit more details. And I'm just checking for a couple more minutes. Oh, here, did I? So I missed one question. Thank you so much, Matthew, for bringing this. Any comments about prematurely wearing the units, since it will also be heating as opposite to just cooling?
Yeah, that's a fantastic question. We've done some testing, just internally to Train, and we haven't seen a huge impact on it. But the expectation would be that it would wear faster than a DX only unit. Your compressor, especially, is going to be running for more hours. So if you're doing heating and cooling, we would expect it to do more. Now, whether or not that changes your asset allocation and how you're kind of doing your asset planning, I think that's going to depend on where and what you're using the equipment for. Some people run equipment into the ground till it's 35 years old, and they're going to have to replace it probably at 20 years, maybe instead. But others have kind of planned replacements already, and they're replacing it every 20 years, and maybe the unit is okay to stay at 20 years. So I think it's going to depend on yourself and what you're already doing from your asset replacement plans. But just common sense, I think I would definitely expect the unit itself to either need a compressor replacement at some point, or or do an equipment replacement earlier if you're doing more work with the compressor. Now, if you think the rest of the unit is operating the same way, right? So it's not really changing much. It's just that refrigerant loop is working now in heating and cooling. But if you have gas backup or electric backup, that part doesn't really change. And the unit, from a rusting perspective and kind of longevity of the unit itself, you shouldn't see much change either, because it's still moving air the same amount. Supply fan's still doing the same thing. It's really that refrigerant loop that that's getting more work.
Here, another comment that I missed, this was earlier, and it's regards to the retrofit system for lower hot water temperature applications. We often look at the changing the connections to a change over coil, so 2-pipe system versus the original 4-pipe system, so that the larger cooling coil is now able to be used as a hot water coil. Thanks, Chad,
absolutely.
For this comment.
Yeah, we do that quite a bit, and it's a great method. You just have to be knowledgeable that you're moving from a 4-pipe to a 2-pipe in that specific unit, but it can make retrofitting a lot easier and faster, and almost the same level of comfort often. But it's totally dependent on the building and the design, and that's why it's great to pull in like we'll come and look at your systems with you. Like, that's one benefit of Trane, is like, we are the manufacturer, we make all these products, but we do actually help our clients like quite a bit. And like, even on the municipal side, like if you have projects you're working on, include us, and we're happy to help you out. Like, you're at the end of the day, like, you're gonna work with a contractor and a consultant kind of to put things together, but having Trane, like, we can be a partner or help you out on projects, and we bring a lot of expertise that's kind of different than your consultant and the contractors that you work with. So it creates a good team to support you.
Thanks so much. Kieran, if you wanna actually ask your question, you have that opportunity, because it's a bit longer.
Sure.
Yeah.
Can you guys hear me?
Yes.
I can hear you.
Perfect. This is just nothing to do with the great presentation, but I was just wondering what future zero carbon technology could look like. So something like a geothermal microbial heat exchange. So below the building, you embed a network of pipes containing a solution of heat-loving microorganisms. These microbes thrive in the subsurface and produce heat. And then we harness that heat and use it for space heating. Like, something, is this, just wanted to know, is this too sci-fi? Is it possible? Is it kind of fantasy?
I mean, I think anything's possible. Every day I learn new technologies, and I mean, even at Trane, we're working on a ton of new stuff every day. That specific example, I guess the key questions I would ask right away are, if we're using microbial heat, and I can think of a couple examples of like microbes that do produce heat, just from my own like environmental background, but if we're doing that, like, the amount of microbes we need to produce enough heat to heat the building is pretty large. But if we can do it, like, I think that's awesome. It's very, very cool idea, very cool technology, something that would definitely want to look at. But do we have the space, and is it feasible? And then what do you do with that heat the rest of the year? Because those microbes can't die. You need like, one of the big problems in Canada especially is that we're not consistent, right? We're very cold, very hot, up and down temperatures every day. The benefit of the storage source heat pump like solution with those tanks that I was showing you is like, they're modular and easily changeable, and every day they can change hot, cold, where is what we get a lot seasonality wise. Like, we see a lot of buildings that are heating in the evening and morning, and then they're cooling in the afternoon, wasting a ton of energy. So storing that heat and using it at a different time, we find really efficient. Whereas if you had the microbes, for example, if they're just eating whatever you're feeding them, and obviously you don't want that to be a low carbon source, however you're feeding them, but if they're just eating something making heat, where does that heat go the rest of the year? Because it's good for part of the year, but like the winter. But then in the summer, what do you do? And in the seasonal times, what do you do? And do you size the amount of microbes for the peak, or do you size them for somewhere in the middle? What do you do at the peak then if you need more heat? Those are the questions that I would be asking. It's a very cool idea, but I think there's a lot of risks and things that I would need to think about. But it's an exciting idea to look into.
Thank you.
You're welcome. Thank you.
And I think with this, we're ending our webinar. Thank you so much, Lucas. This was a lot. Thank you so much for answering all the questions and
You're welcome.
for the
Thank you.
presentation. Thanks everyone who participated and stay with us until the end. And enjoy the rest of the day. I hope it's sunny where you are and you can catch that sun rays before the end of the day. Enjoy the rest of the day and stay tuned for more of our upcoming events. Thank you so much, Lucas.
Thank you. Great to meet everyone. Take care.
Bye.
Thank you.